Welcome to Sleeping Researcher, your peaceful gateway to the wonders of science, gently narrated to help you drift into restful sleep. Tonight, we embark on a serene journey into the mysteries and boundaries of modern physics, a realm where the very fabric of reality stretches beyond our everyday experience. Modern physics invites us to explore the unseen, the incredibly small, and the unimaginably vast. From the strange behavior of quantum particles to the enigmatic forces shaping the cosmos, these mysteries challenge our understanding and inspire endless curiosity. As you listen, allow your mind to wander softly through concepts that push the limits of human knowledge, while your body relaxes deeper with each word. This channel is dedicated to narrating scientific ideas in a calm, soothing voice designed to ease your mind and guide you gently toward peaceful sleep. If you enjoy this tranquil exploration of physics, please consider liking the video and subscribing to Sleeping Researcher. Your support helps us continue sharing these quiet voyages through science, perfect for unwinding after a busy day. Now, settle into comfort as we begin to unfold the delicate layers of modern physics, inviting you to rest while your imagination floats softly through the mysteries at the edge of our understanding. Imagine standing beneath a vast night sky, its endless expanse dotted with stars that have traveled across unimaginable distances to meet your gaze. This simple moment of quiet observation echoes the grand pursuit of physics, a journey to understand the universe in all its complexity and mystery. Modern physics invites us to peer beyond the familiar and explore realms where classical intuition falters and new laws govern the behavior of matter, energy, space, and time. It is within this ever-expanding universe of inquiry that our understanding of reality is continuously challenged and reshaped. Each discovery opens new questions, urging us to delve deeper into the fabric of existence, inspiring a profound sense of curiosity and wonder. As we embark on this exploration, we are reminded that the boundaries of physics are not fixed, but fluid, expanding with every insight gained and every mystery unveiled. Modern physics stands at the crossroads of the known and the unknown, a field where classical concepts give way to quantum strangeness and relativistic intricacies. It reveals a cosmos that often defies everyday experience, where particles exist in multiple states simultaneously, and time itself is malleable. These revelations compel us to rethink fundamental assumptions about reality. At the same time, physics seeks coherence, weaving a tapestry from the smallest subatomic particles to the vast cosmic structures that populate the universe. The quest to unify these disparate scales into a harmonious understanding remains one of science's most profound challenges. As researchers probe the edges of knowledge, they encounter phenomena that resist easy explanation, reminding us that the universe still holds secrets beyond our current grasp. The mysteries of modern physics are not merely abstract puzzles, but gateways to deeper insight into nature's workings, concepts such as dark matter and dark energy, which together constitute the majority of the universe's mass energy content, challenge us to reconsider what lies beyond visible matter. Meanwhile, the peculiar behaviors observed at quantum scales push the limits of measurement and observation, revealing a reality that is fundamentally probabilistic rather than deterministic. These boundaries between what we know and what remains elusive create a dynamic landscape where theory and experiment continually inform one another. It is within this delicate interplay that the beauty of physics emerges, a discipline that embraces uncertainty and complexity while seeking elegant and unifying principles. As we contemplate these frontiers, it becomes clear that modern physics is more than a collection of theories. It is a living dialogue between humanity and the cosmos. Each breakthrough not only extends our scientific horizons, but also reshapes philosophical perspectives on existence and our place within the universe. The pursuit of understanding through physics exemplifies a timeless human impulse to seek meaning and order amid the vast unknown. With every step forward, the journey reveals new landscapes of thought, inviting us to remain open to wonder and discovery as we continue to explore the mysteries and boundaries that define the universe. For centuries, the universe was understood through the lens of classical physics, a framework largely shaped by the remarkable insights of Isaac Newton. His laws of motion and universal gravitation offered a coherent and elegant description of the physical world, one that could predict the motion of planets, the trajectory of projectiles, and the behavior of everyday objects with remarkable precision. This Newtonian worldview, grounded in determinism and absolute space and time, provided a reassuring sense of order to the cosmos. Yet, as the 19th century gave way to the 20th, subtle discrepancies began to emerge, phenomena that defied explanation within the classical paradigm. Light, once thought to be purely a wave, revealed particle-like properties, and atoms, once considered indivisible, displayed internal structures and behaviors that challenged existing notions. These anomalies signaled that classical physics, while profoundly successful, was an incomplete story, a chapter that needed to evolve to encompass the deeper, more intricate nature of reality. This evolution came in the form of two revolutionary theories: quantum mechanics and the theory of relativity. Quantum mechanics introduced a fundamentally different perspective, one that embraced probability and uncertainty as intrinsic features of the microscopic world. Rather than a clockwork universe, it painted a picture of particles existing in states of superposition, where their properties became definite only when observed. Meanwhile, Albert Einstein's theory of relativity challenged the absolutes of space and time, proposing instead that these dimensions are interwoven and relative to the observer's motion. His insights revealed that time could dilate and lengths contract, profoundly altering our understanding of the fabric of reality. Together, these theories dismantled the classical edifice and ushered in a new era of scientific thought, one characterized by its openness to paradox and the unexpected. The transition from classical to modern physics was not merely a scientific revolution, but also a profound philosophical shift. It compelled us to reconsider the nature of knowledge itself, how we observe, measure, and interpret the universe. The certainty once afforded by Newtonian mechanics gave way to a world where probability, observer effect, and the limits of measurement play crucial roles. This shift also blurred the boundary between the observer and the observed, suggesting a deep interconnectedness that continues to inspire debates about the role of consciousness in the physical world. In this way, modern physics expands not only our empirical understanding, but also invites us into a richer dialogue about the essence of reality and our place within it. Yet, even as quantum mechanics and relativity have profoundly shaped our comprehension, significant mysteries remain. The reconciliation of these two frameworks into a unified theory remains elusive, a challenge that lies at the heart of contemporary physics. Concepts such as dark matter, dark energy, and the very origins of the universe hint at deeper layers of reality, still waiting to be uncovered. The boundaries of modern physics are thus defined not by final answers, but by the ongoing quest to explore the unknown, to question assumptions, and to expand the scope of what is scientifically conceivable. It is within this dynamic landscape that the spirit of inquiry continues to thrive, urging us to embrace complexity and uncertainty as we journey further into the cosmos. At the heart of modern physics lies quantum mechanics, a theory that reveals the strange and often counterintuitive behaviors of particles at the smallest scales imaginable. Unlike the familiar world governed by classical physics, where objects have definite positions and predictable motions, the quantum realm defies such straightforward descriptions. Here, particles exist in a haze of probabilities, their exact locations and momenta not fixed, but represented by a mathematical construct known as the wave function. This concept challenges our everyday experience, suggesting that reality at the microscopic level is fundamentally uncertain. The principle of superposition, for instance, allows quantum entities to exist in multiple states simultaneously until observed, a phenomenon that has been experimentally verified yet remains deeply puzzling. Such behaviors are not mere curiosities, but form the foundation of technologies like semiconductors and lasers, underscoring how quantum mechanics bridges abstract theory and practical application. Another hallmark of quantum mechanics is entanglement, a phenomenon Albert Einstein famously dubbed spooky action at a distance. When particles become entangled, their properties become linked in such a way that the state of one instantaneously influences the state of another, regardless of the distance separating them. This interconnectedness defies classical notions of locality and causality, opening profound questions about the nature of information and reality itself. Experiments have confirmed entanglement to extraordinary precision, inspiring new fields like quantum information science and quantum computing. Here, the manipulation of entangled states promises to revolutionize computation and secure communication, revealing how the mysteries of the quantum world continue to inspire innovation. Yet, despite these advances, the full implications of entanglement and other quantum phenomena remain a subject of intense philosophical and scientific debate. reminding us that the microscopic world operates under rules that challenge our deepest intuitions. The boundaries of quantum mechanics are also marked by the unresolved question of measurement. How does the act of observation cause a quantum system to collapse from a superposition of possibilities into a definite state? Various interpretations attempt to address this, from the Copenhagen interpretation, which embraces the central role of measurement, to many worlds theories that propose the continual branching of realities. Each interpretation carries profound implications for our understanding of consciousness, reality, and the limits of scientific explanation. This unresolved tension highlights the delicate balance between mathematical formalism and philosophical inquiry that characterizes the ongoing exploration of quantum theory. It is here, at the intersection of physics and metaphysics, that the mysteries of the infinitely small invite us to reconsider the very nature of existence and observation. As we delve deeper into the quantum domain, experiments continue to push the frontiers of what is observable and controllable. Advances in technology now allow physicists to isolate and manipulate individual atoms, photons, and electrons, probing phenomena once thought purely theoretical. These experimental achievements not only test the limits of quantum mechanics, but also pave the way for new discoveries that may one day clarify its connection to gravity and the large-scale structure of the cosmos. The quest to unify quantum mechanics with general relativity remains one of the most profound challenges in science, suggesting that our current understanding is but a glimpse of a more comprehensive framework yet to emerge. Thus, the quantum world stands as both a testament to human ingenuity and a reminder of the vast unknowns that continue to inspire scientific curiosity. At the heart of modern physics lies a concept both elegant and perplexing: wave-particle duality. This cornerstone of quantum mechanics reveals that entities we once considered distinct, waves and particles, are in fact two complementary aspects of the same reality. Historically, light was understood as a wave, exhibiting behaviors like interference and diffraction, while matter was seen as composed of discrete particles. Yet, as experiments grew increasingly refined, a surprising truth emerged. Photons, the fundamental quanta of light, displayed particle-like properties, capable of delivering energy in discrete packets. Conversely, electrons and other matter particles exhibited wave-like behaviors, spreading out and interfering as if they were ripples on a pond. This duality, defying classical logic, challenges our intuitive notions and forces a re-evaluation of the nature of reality itself. The implications resonate deeply within physics, prompting the development of new mathematical frameworks that describe particles as probability waves rather than tiny billiard balls moving along fixed trajectories. The famous double-slit experiment stands as a vivid illustration of wave-particle duality's mystery. When particles such as electrons are fired one by one through two narrow slits, they produce an interference pattern characteristic of waves. even though each electron seems to arrive as a localized particle. This paradoxical outcome suggests that each particle does not travel through just one slit or the other, but rather exists in a superposition of states, interfering with itself as if it simultaneously explores multiple paths. Only upon measurement does this wave-like probability collapse into the definite position of a particle. Such behavior defies classical expectations and highlights the fundamental role of observation in quantum phenomena. The dual nature of light and matter thus reveals a universe far stranger than everyday experience, where certainty gives way to probabilities and observation shapes reality. Beyond its conceptual intrigue, wave-particle duality has practical consequences that underpin much of modern technology. Devices such as electron microscopes exploit the wave properties of electrons to achieve resolutions far beyond what light waves alone could provide. Similarly, the principles of duality form the foundation for quantum computing, where the superposition of states enables processing capabilities unattainable by classical computers. Researchers continue to probe this boundary between wave and particle, seeking to understand how these dual aspects arise from deeper physical laws. Some theories propose that particles are excitations of underlying quantum fields, bridging the divide between wave and particle descriptions. Investigating these questions not only enriches our understanding of quantum mechanics, but also nudges us toward a more unified picture of nature's fundamental forces. The mysteries of wave-particle duality also highlight the philosophical challenges inherent in interpreting quantum mechanics. Various interpretations attempt to explain how and why particles exhibit dual behavior, from the Copenhagen interpretation's emphasis on measurement to many worlds theories suggesting branching realities. Each framework offers a different perspective on the nature of existence and the role of the observer, yet none can be conclusively proven or disproven with current experimental techniques. This openness invites reflection on the limits of human knowledge and the subtle interplay between theory, experiment, and reality. In this way, wave-particle duality serves not only as a scientific puzzle, but also as a profound meditation on the boundaries of understanding and the continuing journey of discovery. As our exploration of wave-particle duality deepens, it becomes clear that this phenomenon is but one facet of the broader quantum landscape, where classical intuition often falters. The dual nature of light and matter challenges us to embrace a more nuanced view of the physical world, one shaped by probability and interconnection rather than certainty and isolation. This perspective lays the groundwork for further inquiries into entanglement, non-locality, and the unification of quantum theory with the fabric of space-time. With each insight gained, the mysteries of physics expand, inviting us to contemplate not only what is known, but also the vast horizons that remain just beyond our grasp. At the heart of quantum mechanics lies a profound revelation about the nature of measurement itself. The uncertainty principle, formulated by Werner Heisenberg in the early 20th century, tells us that there are fundamental limits to how precisely we can know certain pairs of physical properties simultaneously. Most famously, this applies to a particle's position and momentum. When we try to measure the exact location of a particle, the more precisely we pinpoint its position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our instruments or experimental design, but rather a fundamental property of the universe at microscopic scales. This principle challenges the classical notion that the world is composed of objects with definite properties at all times, independent of observation. Instead, it suggests that at the quantum level, reality is intertwined with the act of measurement itself, blurring the lines between observer and observed. Such a shift in understanding invites us to reconsider what it means to know something in the physical world, where certainty gives way to probability and potentiality. The mathematical expression of Heisenberg's uncertainty principle reveals a relationship governed by Planck's constant, a fundamental quantity in quantum physics. This tiny number sets the scale at which quantum effects become significant, marking a boundary where classical intuition no longer applies. In practical terms, the principle places a fundamental limit on the precision achievable in experiments involving particles such as electrons or photons. When physicists use instruments like particle accelerators or electron microscopes, they must contend with this inherent fuzziness. It is not simply a matter of improving technology, rather, the universe itself imposes a veil that cannot be lifted. This boundary between what can and cannot be known with precision reveals a deep, intrinsic feature of nature, rather than a shortcoming of human inquiry. It hints at a reality where uncertainty and indeterminacy are built-in aspects, shaping the behavior of matter and energy at the smallest scales. Beyond its technical implications, the uncertainty principle carries profound philosophical weight. It implies that at the quantum level, the universe resists a fully deterministic description. This has led to rich discussions about the nature of reality, the role of the observer, and the limits of scientific knowledge. The principle undermines the classical ideal of a clockwork universe, where every event could be predicted if one had complete information. Instead, it introduces an elemental unpredictability, a fundamental openness to chance that permeates the quantum world. This uncertainty does not simply reflect ignorance, it is woven into the fabric of existence, suggesting that the universe itself is not a fixed tableau, but a dynamic process of becoming. Such insights challenge us to expand our understanding of causality and the interplay between knowledge and reality. The ramifications of the uncertainty principle extend into many areas of modern physics, influencing how we think about fields as diverse as quantum computing, particle physics, and cosmology. It sets limits on what can be simultaneously known about particles that form the building blocks of matter, thereby shaping the framework within which scientists operate. These boundaries inspire new approaches to probing the quantum world, encouraging innovative experimental designs that respect the fundamental constraints imposed by nature. In this way, the uncertainty principle acts both as a guide and a reminder that the mysteries of the microscopic realm will always invite deeper exploration, balanced by an acceptance of nature's inherent limits. It is within these confines that the dance of particles and waves continues, revealing a universe rich with complexity and subtlety. As we consider the uncertainty principle alongside other quantum phenomena such as entanglement and superposition, the picture that emerges is one of a universe more intricate and interconnected than classical physics ever imagined. The boundaries imposed by Heisenberg's insight do not close off inquiry, but rather open new pathways to understanding. Each limit encountered encourages us to ask fresh questions, to seek novel perspectives, and to embrace the uncertainty that lies at the core of reality itself. Moving forward, this perspective prepares us to delve deeper into the enigmas of quantum theory and its profound relationship with the structure of space-time, where even more subtle mysteries await. Among the many puzzling phenomena that quantum physics presents, entanglement stands out as one of the most profound and mysterious. When two particles become entangled, their properties become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are separated in space. This connection defies our classical understanding of locality, where objects interact only through direct contact or signals traveling at finite speeds. The term spooky action at a distance, coined by Albert Einstein, captures this unease, as entangled particles seem to communicate instantaneously, challenging the very fabric of cause and effect. The implications of this phenomenon ripple through our understanding of reality, suggesting that the universe operates on principles that transcend ordinary space and time. It is as if entangled particles share information in a realm beyond the limits of classical communication, hinting at a deeply woven tapestry of relationships that bind the cosmos together in unexpected ways. To appreciate the strangeness of entanglement, consider a pair of photons whose polarizations are intertwined. Measuring the polarization of one photon immediately determines the polarization of its partner, regardless of the distance between them, whether meters or light years apart. This instantaneous correlation occurs without any known signal traveling between the two, defying the speed limits set by Einstein's theory of relativity. Such behavior has been experimentally verified through increasingly sophisticated tests, closing loopholes that once left room for classical explanations. The persistent success of these experiments affirms that entanglement is not a mere curiosity, but a fundamental feature of the quantum world. These results have profound consequences for technology as well, laying the groundwork for quantum computing, secure communication, and new methods of information processing that harness entanglement's remarkable properties. Yet, the underlying nature of the connection remains elusive, inviting us to rethink the boundaries of space, time, and information itself. The philosophical implications of entanglement extend beyond physics, touching on questions about the nature of reality and the limits of human knowledge. If particles can remain connected across vast distances without any physical medium, what does this say about the separateness of objects and the flow of time? Some interpretations of quantum mechanics suggest that entanglement reveals a holistic nature to the universe, where parts cannot be fully described independently of the whole. Others propose that reality might be fundamentally non-local, or that hidden variables yet to be discovered could account for these correlations. Despite decades of inquiry, no consensus has emerged, and entanglement continues to challenge our deepest intuitions about how the world works. This enduring mystery propels physicists and philosophers alike to explore new frameworks that might reconcile entanglement with the broader tapestry of physical law. As we contemplate the enigma of entanglement, it becomes clear that modern physics is pushing the boundaries of what we perceive as possible, urging us to expand our conceptual horizons. The connection between entangled particles hints at a universe that is not merely a collection of isolated parts, but an intricately connected whole. This perspective invites us to explore the interplay between quantum mechanics and the structure of space-time, where gravity and quantum effects intertwine in subtle and complex ways. Emerging theories, such as those attempting to unify quantum physics with general relativity, often draw upon the mysterious qualities of entanglement to build bridges across seemingly incompatible domains. In this light, entanglement is not just a curious phenomenon, but a vital clue in the quest to understand the fundamental nature of reality. As we journey further into the depths of modern physics, we encounter one of its most profound revelations: Einstein's theory of relativity. This elegant framework reshaped our understanding of space and time, showing us that these concepts, once thought to be absolute and separate, are in truth woven together into a single fabric. Relativity teaches us that space and time are relative to the observer's state of motion, meaning that measurements of distances and durations can differ depending on one's perspective. This realization challenges the intuitive notions we hold about the universe, inviting us to see reality as a dynamic, interconnected continuum rather than a fixed backdrop against which events unfold. It is within this fabric that mass and energy interact, curving space and warping time itself, giving rise to phenomena such as gravitational time dilation, where time flows differently in stronger gravitational fields. The implications of this are not merely theoretical. They have practical consequences that guide the precision of technologies like GPS navigation, where the effects predicted by relativity must be accounted for to maintain accuracy. In this way, relativity bridges the abstract and the tangible, reminding us that our experience of reality is deeply influenced by the geometry of space-time we inhabit. At the heart of Einstein's insight lies the realization that space and time are not independent entities, but aspects of a unified, four-dimensional continuum known as space-time. This fusion means that events are located not just by where they occur, but also when they occur, with time acting as a dimension alongside the spatial ones. Different observers, moving at different velocities, may disagree on the timing and sequence of events, yet these discrepancies are reconciled within the consistent, underlying structure of space-time. This idea departs radically from the classical Newtonian worldview, where time was absolute and universal. Instead, relativity reveals that simultaneity is relative, and the universe is more fluid and interconnected than previously imagined. The curvature of space-time caused by mass and energy leads to gravity not as a force acting at a distance, but as a manifestation of geometry itself. Objects follow paths dictated by this curvature, moving along what are called geodesics, the straightest possible lines in a curved space-time. This geometric interpretation offers a profound perspective on the nature of gravitational interaction and the fabric of the cosmos. As we reflect upon this, we begin to appreciate how relativity transforms our understanding of motion, causality, and the very framework within which all physical phenomena take place. While special relativity addresses the behavior of objects in uniform motion and reveals the relativity of simultaneity and time dilation, general relativity extends these concepts to include acceleration and gravity, providing a comprehensive description of the gravitational interaction. This theory predicts remarkable phenomena such as black holes, where space-time curves so intensely that not even light can escape, and the expansion of the universe, which shapes the cosmic evolution we observe. These predictions have been confirmed through countless experiments and observations, from the bending of starlight around the sun during eclipses to the detection of gravitational waves rippling through space-time. Yet, despite its successes, general relativity also brings to light the boundaries of our current understanding. At singularities like those inside black holes, or the conditions at the universe's origin, the theory confronts infinities and breakdowns, signaling the need for a deeper, more unified description of nature. The challenge remains to reconcile these relativistic insights with the quantum realm, where the probabilistic nature of particles and forces plays out on the smallest scales. This tension underscores the ongoing quest to unravel the mysteries of space-time and gravity, encouraging us to seek new theories that merge these pillars of modern physics. Time dilation is one of the most intriguing consequences of Einstein's theories of relativity. It reveals that time is not an absolute, unchanging backdrop, but instead can flow at different rates, depending on an observer's relative motion or position in a gravitational field. According to special relativity, when an object moves at speeds approaching the speed of light, time for that object slows down relative to a stationary observer. This effect means that a clock traveling on a fast spacecraft would tick more slowly compared to one on Earth. Similarly, general relativity predicts that time runs more slowly in stronger gravitational fields. This gravitational time dilation has been confirmed through precise measurements, such as comparing clocks at different altitudes on Earth. These insights challenge our everyday intuition and invite us to reconsider the nature of time itself. These revelations about time are not merely theoretical curiosities, but have practical impacts that touch our daily lives in surprising ways. One of the most tangible applications of time dilation is found in the Global Positioning System, or GPS, which serves as a vital technological infrastructure worldwide. GPS satellites orbit Earth at high speeds and experience weaker gravitational pull compared to devices on the planet's surface. Consequently, their onboard atomic clocks run at a different rate than identical clocks on Earth, affected by both special and general relativistic effects. Without correcting for these differences, the position calculations provided by GPS would quickly become inaccurate. leading to errors of several kilometers within a day. Engineers and scientists must, therefore, incorporate relativistic corrections into the system's algorithms to ensure the precision we now take for granted in navigation, mapping, and countless applications relying on GPS. This practical embodiment of time dilation showcases how abstract physics principles weave seamlessly into the fabric of modern technology. It is a profound reminder that the universe's fundamental laws govern even the tools we use to explore it. Beyond technology, time dilation invites deeper philosophical reflection about the nature of reality and our place within space-time. If time can stretch and contract depending on speed or gravity, then the concept of a universal present moment dissolves. Each observer inhabits their own local flow of time, shaped by motion and gravitational environment. This raises profound questions about simultaneity, causality, and the interconnectedness of events across the cosmos. The realization that time is malleable reshapes how we understand the sequence and duration of phenomena, from subatomic processes to cosmic evolution. It also hints at the limits of human perception, confined as we are to experience time in a linear and uniform way. The mysteries of time dilation thus encourage us to expand our imagination and scientific inquiry beyond conventional boundaries. They beckon us toward new horizons of understanding in the quest to unify relativity with quantum theory. As we contemplate the subtle yet profound ways in which time bends and flows, it becomes clear that modern physics continually challenges our assumptions about the universe. The interplay between speed, gravity, and time reveals a dynamic space-time fabric that responds to matter and energy in intricate ways. Yet, many questions remain open. How does time behave at the quantum level, where uncertainties and probabilities dominate? What new principles might emerge from a successful theory of quantum gravity that seamlessly blends the relativistic and quantum realms? These frontiers of knowledge inspire ongoing research and exploration, inviting us to probe ever deeper into the mysteries of existence. In this unfolding journey, time dilation stands as both a remarkable discovery and a gateway to the unknown, guiding us into the next chapters of modern physics. At the frontier of astrophysics lie black holes, enigmatic regions where gravity exerts its influence to such an overwhelming degree that the very fabric of space and time is stretched and twisted beyond familiar comprehension. These cosmic phenomena arise from the collapse of massive stars, compressing matter into a singularity, a point of infinite density surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. Black holes challenge our understanding because they represent conditions where the known laws of physics, particularly general relativity, are pushed to their limits. Within their depths, space-time curvature becomes so extreme that conventional concepts of distance and duration lose their usual meaning. This invites profound questions about the nature of reality and the behavior of matter and energy. energy under such extraordinary circumstances. The study of black holes has revealed insights into gravity's power, yet they continue to puzzle scientists, as their very existence demands a reconciliation of Einstein's theory with the principles of quantum mechanics. As we peer closer into these cosmic abysses, we find that black holes serve as natural laboratories for exploring the boundaries of modern physics. The event horizon marks a point of no return, where time itself appears to slow and freeze from the perspective of a distant observer. Yet, from the viewpoint of an object falling in, time flows uninterrupted, a paradox that highlights the relativity of observation and the complexities embedded in space-time geometry. This interplay opens pathways to consider how gravity might ultimately be unified with quantum effects, a challenge known as the problem of quantum gravity. Black holes also raise questions about information preservation, as the fate of matter and knowledge absorbed by them remains a subject of intense debate. Does information disappear forever, violating quantum laws, or is it somehow encoded on the horizon? Such mysteries spur new theoretical developments and inspire refinements in how we conceive the universe's fundamental workings. Through these inquiries, black holes emerge not merely as cosmic curiosities, but as profound gateways to deeper understanding. The influence of black holes extends beyond their immediate vicinity, shaping the evolution of galaxies and the large-scale structure of the cosmos. Supermassive black holes, residing at the centers of most galaxies, including our own Milky Way, exert gravitational forces that govern stellar orbits and drive energetic phenomena such as quasars and jets of high-energy particles. These immense objects, millions or billions of times the mass of our Sun, hint at complex interactions between matter, energy, and the space-time continuum on scales both vast and minuscule. Their study combines observational astronomy with theoretical physics, leveraging tools such as gravitational wave detectors and high-resolution telescopes to capture signals that inform our models. Each discovery about black holes adds a piece to the intricate puzzle of how gravity, quantum effects, and cosmic evolution intertwine. It is in this delicate balance between observation and theory that modern physics continues to expand its horizon. The mathematical models describing black holes, primarily derived from Einstein's general relativity, present elegant yet incomplete pictures, while the theory predicts the existence of singularities. Where density and curvature become infinite, it cannot fully describe the quantum nature of these regions. This limitation signals the need for a more comprehensive framework that unites the macroscopic and microscopic realms. Efforts such as string theory and loop quantum gravity propose mechanisms to resolve these singularities, suggesting that at the smallest scales, space-time itself may be discrete or composed of fundamental strings. These approaches, though still under development, offer promising avenues to understand how gravity behaves in the quantum domain. The mysteries of black holes thus embody the tension and potential synergy between the known and the unknown, inviting us to reconsider the very fabric of the cosmos from new perspectives. As we continue to study these profound entities, we edge closer to unraveling the deeper laws that govern existence. In exploring black holes, we confront the limits of human knowledge and the infinite possibilities that lie beyond. These regions where gravity warps space-time to its extremes challenge the boundaries of established theories, urging scientists to innovate and rethink foundational principles. The journey into the heart of black holes is not solely about understanding these singular phenomena, but also about seeking a unified description of nature's forces. It is here, at the edge of known physics, that the mysteries of the universe unfold, inviting ongoing curiosity and discovery. As our comprehension deepens, new questions arise, guiding the next steps in our quest to illuminate the cosmos' most profound secrets. In the early 1970s, a remarkable insight emerged that forever altered our understanding of black holes. Stephen Hawking, combining the principles of quantum mechanics with the gravitational framework of general relativity, proposed that black holes are not entirely black. Instead, they emit a faint glow of radiation, now known as Hawking radiation. This subtle phenomenon arises from quantum effects near the event horizon, the boundary beyond which nothing is thought to escape. Virtual particles, which constantly pop into and out of existence in empty space, can be separated by the intense gravitational field at this boundary. One particle may fall into the black hole while its partner escapes, creating the appearance that the black hole itself is radiating energy. This concept elegantly bridges the realms of the very small with the cosmic scale, hinting at a deeper unity in the laws of physics. Such a revelation challenges the traditional view that black holes are eternal and unchanging, suggesting instead that they can slowly lose mass and eventually evaporate over unimaginable spans of time. The implications of Hawking radiation extend far beyond the fate of black holes. It raises profound questions about the nature of information in the universe. According to classical physics, information that falls into a black hole is lost forever, violating the principles of quantum mechanics, which assert that information must be preserved. The discovery that black holes can emit radiation suggests that information might be encoded in this radiation, leading to what is known as the black hole information paradox. This paradox remains one of the most compelling mysteries in modern theoretical physics, driving researchers to explore new frameworks that reconcile gravity with quantum theory. Efforts to resolve this paradox have led to investigations into holographic principles and the very fabric of space-time itself, pointing toward a future where our understanding of reality becomes more interconnected and nuanced. Hawking radiation also invites us to reconsider the boundaries between different scientific disciplines. Where gravity dominates the cosmic dance of galaxies and black holes, quantum mechanics governs the smallest particles and their interactions. The prediction that black holes radiate reveals an intimate dialogue between these two realms, suggesting that a complete theory of quantum gravity may be within reach. This unification is one of the most ambitious goals in physics, promising to illuminate not only black holes, but the origins of the universe and the fundamental structure of matter and energy. As scientists continue to probe these ideas through advanced theoretical models, astrophysical observations, and experiments, the mysteries surrounding black holes serve as a beacon, guiding us toward a deeper, more unified comprehension of nature itself. The subtle emission of Hawking radiation is extraordinarily difficult to detect directly, as it is incredibly faint against the cosmic backdrop. Yet, the theoretical framework it provides motivates innovative approaches to study quantum effects in strong gravitational fields. Laboratory analogues, such as sonic black holes created in ultra-cold gases, offer promising platforms to observe phenomena akin to Hawking radiation, bringing these cosmic mysteries into controlled experimental settings. This blending of theory and experiment enriches our exploration, demonstrating how abstract concepts can inspire tangible advancements in technology and methodology. In this way, the study of black holes and their radiation continues to expand the horizons of human inquiry, revealing new paths where the mysteries of the universe and the boundaries of physics converge. At the heart of modern physics lies the Standard Model, a remarkable theoretical framework that serves as our most detailed map of the subatomic world. It elegantly categorizes the fundamental particles, quarks, leptons, and bosons that compose the fabric of matter and mediate the forces we observe, except for gravity. This model is the culmination of decades of experimental discoveries and theoretical insights, providing a coherent picture of how particles interact through the electromagnetic, weak, and strong nuclear forces. Each particle within this framework has been observed with extraordinary precision, confirming predictions that have withstood the scrutiny of countless experiments. The Standard Model's predictive power is nothing short of astonishing, enabling physicists to anticipate new particles and phenomena before they are experimentally confirmed, such as the elusive Higgs boson discovered in 2012. This triumph underscored the model's robust architecture and its central role in understanding the microscopic universe. Yet, the Standard Model is more than a catalogue. It is a deep narrative about the symmetries and principles governing the quantum realm, revealing a universe that is both intricate and wonderfully orderly. Despite its successes, the Standard Model leaves many questions unanswered, highlighting the boundaries of our current understanding. For one, it does not incorporate gravity, the force that shapes the cosmos on the grandest scales, hinting at a deeper theory yet to be discovered. Moreover, the model does not explain the nature of dark matter, an invisible substance that influences the motion of galaxies and the evolution of the universe. Neutrinos, those ghostly particles that barely interact with matter, also challenge the completeness of the model, exhibiting tiny masses that the Standard Model cannot fully account for. These gaps inspire physicists to look beyond the established framework, searching for new principles or particles that could extend or supersede it. This sense of incompleteness does not diminish the Standard Model's significance. Rather, it emphasizes the dynamic and evolving nature of scientific knowledge, inviting continued exploration and refinement. In laboratories around the world, powerful particle accelerators and detectors probe deeper into the subatomic realm, testing the Standard Model's limits with ever-increasing precision. Experiments at facilities like the Large Hadron Collider continue to search for phenomena that may hint at physics beyond the Standard Model. Subtle deviations in particle behavior, rare decay processes, or entirely new particles. These efforts are complemented by astrophysical observations, where cosmic rays and neutrino telescopes provide alternative windows into fundamental physics. Together, these approaches weave a rich tapestry of data that guides theoretical advancements, encouraging physicists to unify quantum mechanics with gravity or to incorporate new symmetries and dimensions. The pursuit of such unifying frameworks remains one of the most profound quests in modern physics, promising to deepen our understanding of the universe's underlying principles. The Standard Model, in this light, represents both a triumph and a threshold. It encapsulates our most comprehensive knowledge of particle physics to date, yet it stands as an invitation to venture beyond known boundaries. The theoretical elegance and experimental verification it embodies remind us of the power of human curiosity and ingenuity. At the same time, the mysteries it leaves unresolved serve as beacons, guiding future generations of scientists toward new discoveries and revolutionary ideas. This delicate balance between certainty and mystery is the essence of scientific progress, a continuous journey that expands the horizons of understanding while acknowledging the vast unknown that remains. Among the many profound questions in modern physics, one stands out with elegant simplicity. Why do particles have mass at all? The answer to this question remained elusive for decades, nestled within the complex framework of the Standard Model. It was theorized that an invisible field permeates the universe, interacting with fundamental particles to endow them with mass. This concept, now known as the Higgs field, suggested that particles acquire mass by coupling to this omnipresent field. But without direct evidence, it remained a beautiful hypothesis. The search for the tangible signature of this field led scientists to hunt for the particle associated with it, the Higgs boson, a particle that would confirm the mechanism by which mass arises. The discovery of the Higgs boson in 2012 at the Large Hadron Collider marked a monumental achievement, not merely as a new particle found, but as a validation of a cornerstone idea explaining the very fabric of matter. The journey to detect the Higgs boson was a testament to human perseverance and technological prowess. At the Large Hadron Collider, protons were accelerated to near light speed and collided with immense energy, recreating conditions akin to the earliest moments of the universe. Within these collisions, fleeting traces of the Higgs boson could appear, but only for an unimaginably brief instant before decaying into other particles. Detecting such ephemeral signals required sophisticated detectors and immense data analysis, sifting through billions of events to find the subtle hints of the Higgs. When those signals emerged, it was as if a hidden piece of the cosmic puzzle had been revealed, affirming the mechanism by which particles, from electrons to quarks, acquire their mass, and thus the matter that composes the universe. This discovery bridged the gap between theory and observation, reinforcing the Standard Model's robustness while opening new questions about the nature of mass and its origins. Yet, even with the confirmation of the Higgs boson, mysteries linger in the shadows of physics. The mass of the Higgs itself presents puzzles, such as why it has the particular value observed and why the Higgs field interacts differently with various particles. Furthermore, the discovery invites deeper reflections on the stability and fate of our universe as the Higgs field influences cosmic evolution in subtle ways. It also leaves open the question of whether the standard model is complete or merely an effective theory awaiting a more profound framework. Could there be additional Higgs-like fields or entirely new physics lurking beyond the energies we have probed? These questions remind us that each breakthrough in physics is also a portal to new horizons, where the known and unknown intertwine in a delicate dance. Thus, the Higgs boson stands as both a triumph and a threshold, illuminating the path ahead while revealing how much remains to be understood. The discovery of the Higgs boson also resonates beyond particle physics, influencing cosmology and our understanding of the universe's birth and evolution. The Higgs field's uniform presence across space and time shapes how matter coalesced into stars and galaxies, and may even play a role in the mysterious dark energy accelerating cosmic expansion. Moreover, the techniques and technologies developed to find the Higgs have spurred advances in computing, data science, and engineering, demonstrating the profound interconnectedness of fundamental research and practical innovation. In this way, the Higgs boson is a symbol of the intricate interplay between the smallest scales of matter and the vastness of the cosmos, inviting us to contemplate the unity of nature's laws. As we continue to explore these connections, the legacy of the Higgs discovery will inspire new generations to probe the boundaries of knowledge with curiosity and wonder. Beyond the familiar stars, planets, and galaxies that shine brightly in the night sky lies a profound cosmic mystery: dark matter. This elusive substance does not emit, absorb, or reflect light, rendering it completely invisible to traditional telescopes. Yet its presence is undeniable. Dark matter exerts a gravitational pull on visible matter, influencing the motion of stars within galaxies and the movement of galaxies within clusters. Observations of these gravitational effects reveal that the matter we can see accounts for only a small fraction of the universe's total mass. The vast majority remains hidden, cloaked in darkness, compelling scientists to rethink the fundamental composition of the cosmos. Its discovery has reshaped modern physics, challenging existing theories and prompting new questions about the nature of matter and the forces that govern it. The journey to understand dark matter began with perplexing astronomical observations in the early 20th century. Vera Rubin's pioneering studies of galactic rotation curves revealed that stars at the edges of galaxies orbited faster than expected if only visible matter were present. This discrepancy suggested an invisible mass anchoring the galaxies together, preventing them from flying apart. Since then, numerous lines of evidence, from gravitational lensing to cosmic microwave background measurements, have reinforced the dark matter hypothesis. Despite its profound influence on cosmic structure and evolution, dark matter remains undetected by direct means. This has led to a diverse array of theoretical candidates, from weakly interacting massive particles, or WIMPs, to axions and sterile neutrinos, each offering a different glimpse into the potential properties of this invisible majority. The pursuit of dark matter detection continues to drive innovation in experimental physics, pushing the boundaries of technology and imagination. The implications of dark matter extend far beyond astrophysics, touching the core of particle physics and cosmology. If dark matter consists of new, fundamental particles, their discovery would represent a monumental expansion of the known particle zoo, revealing previously uncharted aspects of the universe's building blocks. This prospect excites physicists as it may unlock deeper symmetries or hidden dimensions woven into the fabric of reality. Moreover, understanding dark matter is essential for piecing together the universe's grand narrative, from the formation of the first galaxies to the current large-scale structure spanning billions of light years. It also poses intriguing questions about the very nature of gravity and the potential need for modifications to our current theories. As research advances, the boundary between the known and the unknown continues to shift, inviting us to contemplate the vast tapestry of existence in ever more profound ways. Despite decades of intensive study, dark matter remains one of the most compelling enigmas in science. Its identity concealed, but its influence undeniable. The ongoing search involves a global network of underground detectors, space-based observatories, and particle accelerators, each designed to capture fleeting interactions or subtle signals from this invisible substance. These efforts embody the spirit of scientific inquiry, patient, meticulous, and open to surprises. Through this quest, we not only seek to unveil dark matter itself, but also to deepen our understanding of the fundamental laws that shape the cosmos. In doing so, we confront the delicate balance between what can be observed and what must be inferred, between light and shadow, presence and absence. This interplay underscores the profound humility and wonder at the heart of modern physics. While dark matter reminds us of the unseen scaffolding holding galaxies together, dark energy presents an even more profound mystery, an invisible force causing the universe itself to expand at an ever-accelerating rate. Discovered in the late 1990s through observations of distant supernovae, this unexpected acceleration challenged the long-held belief that cosmic expansion should be slowing down under the pull of gravity. Instead, it revealed a subtle yet pervasive energy permeating all of space, pushing galaxies apart faster with each passing moment. This discovery reshaped our understanding of the cosmos, suggesting that the majority of the universe's energy content is not matter, visible or dark, but this enigmatic dark energy. It compels physicists to reconsider the nature of space, time, and the very fabric of reality. The implications extend far beyond astronomy, reaching into the foundations of physics itself, where quantum theory and general relativity struggle to coexist in a seamless framework. The character of dark energy remains elusive, largely because it does not emit, absorb, or reflect light, leaving no direct means of observation. Scientists infer its presence through its gravitational effects on cosmic structures and the rate of expansion measured across billions of years. Various hypotheses attempt to explain its origin. Some propose it is a cosmological constant, a fixed energy inherent to space itself, while others suggest dynamic fields that evolve over time, akin to the inflaton field that may have driven the rapid inflationary epoch shortly after the Big Bang. Yet, none of these models fully reconcile with current observations or with the known laws governing particles and forces. This persistent ambiguity invites a broader, philosophical reflection on the limits of human knowledge and the methods by which we probe the universe. It challenges researchers to develop innovative experiments and more precise measurements, seeking subtle clues that might reveal the true nature of this cosmic accelerant. Each inquiry opens new avenues of exploration, yet also deepens the mystery, illustrating the delicate interplay between theory and observation. In grappling with dark energy, physicists encounter the boundaries of what is experimentally accessible and theoretically conceivable. Unlike the tangible particles of the Standard Model or the gravitational waves now detected from merging black holes, dark energy's influence is woven into the large-scale structure and destiny of the cosmos itself. It raises profound questions about the ultimate fate of the universe, whether it will continue expanding indefinitely, tear itself apart in a hypothetical Big Rip, or perhaps settle into a steady state. These scenarios depend critically on the properties of dark energy, which remain frustratingly out of reach. The quest to understand this force drives collaborations across disciplines, blending cosmology, particle physics, and astrophysics. It reflects a collective aspiration to transcend the current horizons of knowledge, revealing the universe not only as a physical entity, but as a profound mystery, inviting contemplation and discovery. This journey underscores the humility and persistence inherent in scientific endeavor as we confront both the vastness of space and the subtlety of unseen forces. As we continue to explore the mysteries of dark energy, new generations of telescopes and surveys promise to map the cosmos with unprecedented precision. These instruments aim to track the expansion history and the growth of cosmic structures, seeking subtle deviations that might hint at the underlying physics. Simultaneously, theoretical advances strive to integrate dark energy into a coherent picture that unites gravity and quantum mechanics. A quest that may require revolutionary insights or even new physics beyond current paradigms. The interplay between observation and theory remains delicate, a dance of clues and conjectures that propels the scientific narrative forward. In embracing this unknown, modern physics reveals its most profound characteristic: not certainty, but wonder. Not final answers, but enduring questions. This pursuit of understanding leads naturally toward contemplating the boundaries of reality itself, inviting us to peer deeper into the fabric of existence. At the frontier of theoretical physics lies a profound challenge: to unify the seemingly incompatible frameworks that describe the universe's fundamental workings. On one hand, quantum mechanics governs the behavior of particles at the smallest scales, where uncertainty and probability reign supreme. On the other, Einstein's theory of general relativity offers a geometric description of gravity, shaping the vast cosmos through the curvature of space-time. For decades, these towering pillars of physics have resisted reconciliation, their mathematical languages refusing to merge into a single, harmonious theory. In this landscape of mystery and complexity, string theory emerges as a bold attempt to bridge the divide. Rather than treating fundamental particles as point-like dots, string theory proposes that all particles are in fact tiny, one-dimensional strings vibrating at distinct frequencies. Each mode of vibration corresponds to a different particle, weaving a rich tapestry that encompasses the diverse phenomena observed in nature. By extending the concept of particles into the realm of strings, this framework offers a tantalizing path toward unifying all interactions, including the elusive quantum aspects of gravity. The elegance of string theory lies not only in its mathematical sophistication, but also in its conceptual shift. It suggests that the fundamental constituents of reality are not isolated points, but dynamic entities whose vibrations encode the properties of matter and forces. This perspective challenges our classical intuitions, inviting us to reconsider the fabric of space and time as emergent phenomena arising from deeper, string-like structures. Remarkably, the theory predicts additional spatial dimensions beyond the familiar three, dimensions that may be compactified or hidden at scales far beyond current experimental reach. Such extra dimensions provide the necessary degrees of freedom for the strings to vibrate in ways that produce the rich variety of particles and forces, including gravity. While the complexity of these higher dimensional geometries can be daunting, they are essential to the internal consistency of the theory. In this way, string theory weaves together geometry, quantum mechanics, and gravity into a single conceptual framework, hinting at a more unified understanding of the cosmos. Despite its profound promise, string theory remains a realm of hypotheses and mathematical exploration, rather than experimentally verified fact. Direct empirical evidence is elusive, largely due to the extraordinarily small scales at which strings would operate, many orders of magnitude below the reach of current particle accelerators. This situation places string theory in a unique position within modern physics. It is simultaneously a powerful framework for addressing long-standing puzzles, and a reminder of the challenges inherent in probing nature's deepest layers. Researchers continue to develop new mathematical tools and search for indirect signatures that might hint at the presence of strings or the extra dimensions they imply. Moreover, string theory has inspired unexpected connections between different fields of physics, from black hole thermodynamics to condensed matter systems, revealing a web of interrelated phenomena that enriches our understanding beyond its original scope. This ongoing journey exemplifies the spirit of scientific inquiry, an openness to bold ideas, tempered by the rigorous demand for evidence. In contemplating string theory, we find ourselves at the edge of knowledge, peering into a domain where familiar concepts of particles and forces begin to blur and converge. The theory's ambition to reconcile gravity and quantum mechanics offers a glimpse of a more fundamental description of nature, one that might transcend the limitations of both frameworks. Yet, the path forward is uncertain, marked by intricate mathematics and subtle conceptual challenges that invite both awe and humility. As the theoretical landscape continues to evolve, it encourages us to expand our imagination and embrace complexity, reminding us that the universe may be far stranger and more beautiful than previously conceived. This exploration into the microcosmic vibrations of strings is but one step along the vast road toward understanding, a road that winds through the mysteries and boundaries of modern physics. As we venture beyond the familiar contours of our cosmos, modern physics invites us to entertain a profoundly provocative idea that our universe may be but one among countless others, each with its own distinct realities and physical laws. This concept, known as the multiverse hypothesis, challenges the very notion of a singular universe, stretching the boundaries of scientific inquiry and philosophical reflection alike. Rooted in interpretations of quantum mechanics, cosmic inflation, and string theory, the multiverse suggests a vast, perhaps infinite, ensemble of universes, each born from different initial conditions or branching quantum events. Such a framework could offer explanations for some of the deepest puzzles in physics: why the constants of nature take the precise values they do, or why our universe appears so finely tuned for life. Yet, these ideas remain deeply speculative, residing at the frontier where empirical evidence is scarce and theoretical imagination flourishes. The notion of a multiverse arises naturally in several leading theories of physics. In the context of eternal inflation, for example, our observable universe is but a bubble in a frothy cosmic sea, with other bubbles forming continuously, each potentially housing different physical parameters and laws. Similarly, string theory's landscape of possible solutions hints at an almost unfathomable variety of vacuum states, each corresponding to a distinct universe with its own unique properties. Quantum mechanics, too, contributes to this picture through the many worlds interpretation, where every quantum event branches into multiple outcomes, spawning parallel realities. While these frameworks differ in their details, they converge on a startling implication: the cosmos might be far more vast and variegated than our senses or instruments can detect. Yet, this expanse of possibility also raises profound questions about the nature of reality and the limits of scientific verification. How might we ever test such ideas, and what would it mean for our understanding of existence if the multiverse proves true? The multiverse hypothesis not only expands the scope of physics, but also invites us to reconsider the philosophical foundations of science. Traditionally, science has relied on observation and experiment within a single, shared universe. The multiverse, however, suggests realms forever beyond direct reach, where the traditional criteria of falsifiability and empirical testing become ambiguous. This tension challenges scientists to develop new conceptual tools and subtle, indirect methods to probe these hidden domains. For instance, cosmologists seek signatures in the cosmic microwave background radiation or patterns in the large-scale structure of the universe that might hint at collisions or interactions between bubble universes. Meanwhile, theoretical physicists strive to refine mathematical models that can predict observable consequences of a multiverse framework. This interplay between the known and the speculative nurtures a delicate balance, one that humbly acknowledges the limits of our knowledge while daring to explore the vast unknown. Such is the nature of progress at the frontiers of physics, where mystery and rigor coexist. Embracing the possibility of a multiverse also transforms our cosmic perspective, inviting a sense of wonder and curiosity about the nature of existence itself. If countless universes exist, each with different laws and constants, then the uniqueness of our own cosmos becomes a profound enigma. It prompts us to ask why we find ourselves in this particular universe, with conditions suitable for complexity and life, amid a seemingly infinite array of alternatives. Some interpretations suggest that anthropic reasoning, recognizing that observers can only arise in particular environments, may partially address this question, though it remains a topic of lively debate. Beyond the scientific intricacies, the multiverse challenges our philosophical and even spiritual sensibilities, stirring reflections on identity, reality, and meaning. In facing these vast unknowns, modern physics not only expands its technical boundaries, but also deepens its dialogue with the human experience, weaving together threads of science and wonder. As we continue to explore the tantalizing possibilities of the multiverse, we find ourselves at the threshold of new realms of understanding, where empirical investigation and bold theoretical speculation intertwine. This journey encourages an openness to ideas that once seemed fantastical, reminding us that the pursuit of knowledge often leads beyond the horizon of the known. The multiverse stands as a testament to the evolving nature of modern physics, a discipline always reaching outward, seeking to illuminate the profound mysteries that lie beyond our immediate grasp. In this spirit, we turn now to consider the intriguing implications of quantum entanglement, another phenomenon that challenges our conventional notions of space and time, inviting us to explore the subtle connections woven into the fabric of reality. At the heart of modern physics lies a realm that defies our everyday intuition, a world governed by the principles of quantum mechanics. Here, particles exist in states of superposition, where they can embody multiple possibilities simultaneously and become entangled, exhibiting connections that transcend classical boundaries of space and time. These quantum peculiarities, once considered mere curiosities, are now being harnessed to forge a new era in computation. Quantum computing seeks to exploit these very weird features of the quantum world, not only to perform calculations, but to revolutionize the way information is processed and understood. Unlike classical bits that exist distinctly as zeros or ones, quantum bits, or qubits, embrace the wave-like nature of matter, enabling them to represent a spectrum of states concurrently. This foundational shift offers unprecedented computational power, promising to tackle problems that have long eluded classical machines. The promise of quantum computing extends far beyond mere speed. It opens the door to solving complex problems in cryptography, optimization, and simulation of quantum systems themselves. By leveraging superposition and entanglement, quantum algorithms can explore vast computational landscapes simultaneously, weaving through possibilities in ways that classical computers cannot replicate. This ability to process an exponential number of states at once holds profound implications for fields like materials science, drug discovery, and secure communication. Yet, the path to fully realizing these potentials is paved with intricate challenges. Qubits are inherently fragile, susceptible to environmental disturbances that can collapse their delicate quantum states. The art of maintaining coherence, error correction, and scalable architectures remains a central focus of ongoing research. Despite these hurdles, experimental advances continue to push the boundaries, inching closer to machines capable of outperforming classical counterparts in meaningful tasks. Beyond the technical feats, quantum computing invites us to reconsider the fundamental nature of information itself. It blurs the line between computation and the fabric of reality, suggesting that information processing may be deeply woven into the quantum structure of the universe. As physicists and computer scientists collaborate, they explore not only how to build these machines, but also what their existence reveals about the limits of knowledge and the architecture of nature. This fusion of physics and information theory challenges our classical assumptions, revealing a landscape where computation becomes an intrinsic physical process rather than a mere abstract operation. In this light, quantum computing is more than a technological innovation. It is a manifestation of our deepening understanding of the quantum principles that govern the cosmos. As we stand on the cusp of this quantum revolution, the interplay between theory and experimentation continues to illuminate the subtle boundaries between the known and the unknown. Each new discovery in quantum information science nudges us closer to unraveling the mysteries of entanglement, coherence, and the nature of reality itself. In doing so, it invites us to embrace a worldview where uncertainty and probability are not limitations, but intrinsic features of a richer, more complex universe. With every qubit manipulated and every quantum algorithm tested, we move toward a future where the strange and beautiful principles of quantum mechanics become tools for exploration and innovation. This ongoing journey reflects the spirit of modern physics, ever curious, ever expanding, reaching toward the edges of what can be understood. Despite the remarkable progress made in modern physics, there remain profound mysteries that continue to elude our understanding. The very frameworks that have propelled science forward, from quantum mechanics to general relativity, also reveal their own boundaries, exposing paradoxes and questions that challenge our deepest assumptions. For instance, the reconciliation of gravity with quantum theory remains one of the most elusive quests, a puzzle that hints at an incomplete picture of the universe's fundamental workings. The vast scales of the cosmos and the minuscule realms of subatomic particles each harbor secrets that suggest our current theories, while powerful, are but stepping stones toward a grander, more unified comprehension. This tension between what is known and what remains hidden is not a failure of science, but rather its most compelling invitation to keep exploring, questioning, and refining. Among the most intriguing open questions are those surrounding dark matter and dark energy, which together constitute the majority of the universe's mass energy content, yet remain invisible and largely inscrutable. These phenomena shape the cosmos on the largest scales, influencing the formation of galaxies and the ultimate fate of the universe itself. Yet despite decades of observation and experimentation, their nature continues to defy direct detection and clear explanation. Similarly, the nature of time and space, concepts so fundamental to our experience, pose deep philosophical and scientific challenges. Is time a continuous flow, or does it emerge from more basic, discrete units? Can space itself be quantized, or is it a smooth fabric? These questions highlight the limits of our current instruments and theories, reminding us that the universe may be far stranger and more intricate than even the most imaginative minds have conceived. Another boundary lies within the realm of quantum mechanics itself, where phenomena such as entanglement and superposition challenge classical notions of locality and causality. The famous paradoxes, like Schrödinger's cat or the EPR paradox, invite us to reconsider the nature of reality, measurement, and observation. Is the wave function a mere mathematical abstraction, or does it represent a deeper reality? The quest to understand these foundational issues has led to a variety of interpretations, none universally accepted, each carrying profound implications for how we perceive existence. These enduring debates illustrate that even with precise experimental verification, the interpretation of quantum phenomena remains open-ended, urging physicists to develop new conceptual tools that might one day demystify the quantum world. Beyond the frontiers of microscopic and cosmic scales, the search for a so-called theory of everything continues to inspire generations of scientists. Such a theory would unify the fundamental forces and particles into a single, coherent framework, revealing the underlying simplicity beneath apparent complexity. Yet, attempts to formulate this theory through approaches such as string theory or loop quantum gravity have so far yielded elegant mathematics without definitive experimental confirmation. This gap between mathematical beauty and empirical evidence underscores a fundamental challenge in physics: the balance between theoretical ambition and observational constraint. As new technologies emerge and experimental precision improves, the hope remains that clues hidden in the subtle fabric of reality will guide us toward a deeper synthesis, one that transcends the current boundaries of knowledge. In embracing these mysteries and limitations, modern physics invites us not only to expand our scientific horizons, but also to cultivate a sense of wonder and humility toward the universe. Each paradox and unanswered question serves as a reminder of the intricate tapestry of reality, woven with threads we have yet to fully discern. The pursuit of understanding is an endless voyage, one that challenges us to rethink assumptions and embrace uncertainty as a vital part of discovery. As we continue this journey, the boundaries of knowledge will shift and evolve, shaped by both insight and inquiry. With each step forward, the unknown beckons, promising new vistas of comprehension that await beyond the horizon. As we stand at the threshold of new scientific epochs, the future frontiers of physics beckon with promises both profound and subtle. Emerging technologies and experimental designs are being crafted with meticulous care, reaching sensitivities and scales previously thought unattainable. Particle accelerators, for instance, continue to grow in ambition, designed to probe energies that could reveal particles or forces hidden beyond the standard model. These colossal machines, operating at near light speed, act as microscopes into the fabric of reality, smashing together matter in ephemeral bursts to glimpse what lies beneath. Yet, it is not only size and energy but also precision that defines the next generation of experiments. Quantum sensors harnessing entanglement and coherence are poised to measure gravitational waves and fundamental constants with extraordinary fidelity. Alongside accelerators and sensors, astrophysical observatories continue to play an indispensable role in expanding the horizon of modern physics. New telescopes and detectors scan the skies for signals that may hint at dark matter or dark energy, enigmatic constituents that dominate the cosmos but elude direct detection. By capturing faint whispers of cosmic phenomena, such as the subtle distortions in the cosmic microwave background or the rare interactions of neutrinos, these instruments provide a complementary perspective to earthbound laboratories. In parallel, experiments exploring the quantum properties of space-time itself seek to bridge the gap between general relativity and quantum mechanics. These endeavors, often involving ultra-cold atoms or advanced interferometry, aim to reveal the granular or discrete nature of space and time, potentially rewriting our conception of the universe's very structure. Each experimental advance gently nudges the frontier outward, opening new corridors for inquiry that may illuminate the shadows cast by our current theories. The quest for new physics also embraces the elegance of interdisciplinary collaboration, weaving insights from mathematics, computer science, and engineering into the fabric of experimental design. Machine learning algorithms now assist in parsing vast datasets, uncovering subtle patterns that human analysis might overlook. Quantum computing, still in its infancy, holds promise for simulating complex physical systems that defy classical computation, potentially unlocking deeper understanding of particle interactions and material behaviors. These technological synergies not only enhance our capacity for discovery, but also redefine the methodology of physics itself. They invite us to consider that the next breakthroughs may arise not solely from incremental improvements, but from revolutionary ways of thinking and probing the universe. Such a landscape of innovation fuels both anticipation and reflection as we prepare to confront questions that challenge the very foundations of reality. As these emerging experiments and technologies take shape, they remind us that the pursuit of knowledge is an ever-evolving dialogue between theory and observation. Each new measurement carries the potential to confirm long-standing hypotheses or to reveal surprising anomalies that prompt fresh theoretical frameworks. This interplay underscores the dynamic nature of modern physics, where certainty is provisional and openness to the unknown is essential. The next generations of experiments are thus not endpoints but gateways, inviting us to step beyond the familiar and explore realms where space, time, matter, and energy intertwine in ways yet to be imagined. In this unfolding narrative, curiosity remains our compass, guiding us through the subtle complexities and profound mysteries that characterize the universe's grand design. Pause. As we stand at the edge of our current understanding, it becomes clear that modern physics is less about final answers and more about embracing the intricate dance between what is known and what remains hidden. The universe, vast and enigmatic, invites us to acknowledge the limits of our comprehension, not as barriers, but as catalysts for deeper inquiry. Each mystery we encounter, whether the nature of dark matter, the fabric of space-time, or the unification of quantum mechanics and gravity, serves as a gentle reminder of the humility required in the scientific endeavor. This openness to wonder encourages us to see the cosmos not merely as a puzzle to be solved, but as a profound story unfolding across time and space, with each discovery adding new layers of meaning and awe. The boundaries of modern physics are in many ways frontiers that beckon a future where imagination and rigor coexist harmoniously. The theories we hold today are stepping stones, provisional frameworks that may one day be replaced or refined as new evidence comes to light. This fluidity is not a weakness, but a testament to the strength of the scientific method, a continuous process of questioning, testing, and revising. It is within this process that the beauty of physics truly reveals itself. A discipline that thrives on uncertainty and transforms it into opportunity. By embracing the unknown, physicists and dreamers alike contribute to a legacy of curiosity, ensuring that the quest to understand the universe remains vibrant and ever expanding. Ultimately, the mysteries at the heart of modern physics invite each of us to participate in a shared journey, a collective exploration that transcends cultural and temporal boundaries. The pursuit of knowledge is, at its core, a deeply human endeavor, fueled by our innate desire to connect with the cosmos and find our place within it. As we look ahead, it is this spirit of wonder and perseverance that will carry us forward, inspiring new generations to ask bold questions and seek answers beyond the horizons of today's science. In embracing the mystery of the universe, we cultivate not only understanding, but also a profound sense of belonging to something far greater than ourselves.